So now let's talk about the power rule and exponential and logarithmic functions. So you may be thinking, well, haven't we already covered the power rule for polynomials, and haven't we already covered e to the x and ln x? Well, yes, but let's talk about a couple of other similar cases that we can do. So let's, for example, talk about the following. Let's say we want to have the function 2 to the x. So let's say this is our f at x. So a question is, what is f prime at x? All right, well, what does the graph of 2 to the x look like? Well, I'll draw you the picture, but of course, if we just draw this rough picture without sort of computer-generated precision, it basically just looks like the graph of e to the x. So you might think, well, is this function, 2 to the x, is it also its own derivative? And the answer is no, but of course it's related enough to e to the x that it has to have some similar properties. So how similar are these properties? Well, let me tell you. So 2 to the x, this guy, well, let's do a funny little trick here. We have that 2 is equal to e ln 2. And this is a tricky little thing, but this is happening just by virtue of the fact that 2 is equal to e to the ln 2, because e to the x is the inverse of the natural logarithm of x. So we have this, so that this turns into e ln 2 of x. But now, can we differentiate this guy? Well, the answer is yes. We can differentiate this function with the chain rule. We're going to let u be equal to ln 2 of x, and we're going to let our f of u therefore be equal to e to the x. So we have that, sorry, I used two different things as f, but this will happen in the real world. Let's suffice it to say that if we take d by dx of 2 to the x, this is going to, by the chain rule, be, well, okay, we're taking the derivative of this function e to the x, and we're plugging in ln 2x up top, so this is just going to be e to the ln 2 of x, but then we have to multiply this by the derivative of ln 2 of x. This is just a polynomial, a degree 1 polynomial, so its derivative is just ln 2. So this thing is equal to ln 2 of, now let's rewrite this as 2 to the x. So we've found out how to differentiate via the chain rule 2 to the x, and it's just going to be ln 2 times 2 to the x. And a simple fact is that for a greater than 0, we have that the derivative of a to the x is similarly just going to be natural logarithm of a times a to the x. Now, another thing that you can do is you can compute the derivative of log base a of x in essentially the same way as we did the natural logarithm. Remember that log base a of x is the inverse function of a to the x. So I'll spare you the details, but you can deal with them yourself if you'd like to work through them. But following the argument almost exactly to when we differentiated ln x, using the fact that the derivative of a to the x is not just a to the x, but is ln a times a to the x, we get, for almost identical reasons, that this guy here, his derivative is ln a, 1 over ln a x. Okay, so we can do this, both of these things with the chain rule. So now we know how to differentiate arbitrary exponential functions and arbitrary logarithmic functions. Let's also do a little more in the same vein. Okay, so a similar thing we saw before is we saw, at least for polynomials, we saw that if you wanted to differentiate x to the power n, that's going to give you n times x to the n minus 1. So what is exciting is that it turns out that if you have r, any real number, it's in fact true that you can define a function x to the power r, and it's a differentiable function, and we're going to get that this derivative is actually equal to the most naive guess that you could come up with, just that it's the same as for natural numbers. By the way, just in case if r is negative, we don't, or not negative, by the way, in case r is something like a fraction, we don't necessarily want to take powers of negative numbers, so let's just assume that x is greater than 0 throughout this. Okay, why is this true? Why does this rule hold? Well, this is again going to be a chain rule thing. What we can do is we can just think about what this has to mean and use the chain rule to differentiate it. Well, if we have x to the r, what does this have to mean? Well, a strange way, but an accurate way to write x is e to the ln x. So if you raise that to the r, that's going to be e to the r ln x. So if we want to differentiate x to the r, that's just the derivative of this guy, which we can of course differentiate with the chain rule. Its derivative is, well, first of all, you take the derivative, so the inside guy is r ln x, the outside guy is e to the x. So first of all, you take the derivative of the outside guy and plug the inside guy in. And then you take the derivative of the inside guy, which in this case is just r over x. All right, but now let's rewrite this thing as x to the r. So its derivative is x to the r times r over x. And we can, of course, rewrite this as r times x. There's rx's up here, 1x down there, r minus 1. So that's how this works, okay? So we, in fact, have this generalized version of the power rule, which actually holds for any real number. And now sort of one way that this could show up in an example, let's just do sort of a quick example. An ugly-looking function, but one that we can absolutely differentiate, no problem. Let's let f at x be equal to x plus 2 to the x to the power pi. All right, this is a strange sort of thing. We can't use standard factoring or binomial anything because we're raising this to the power pi. But of course, now that we have this rule here and the chain rule, as well as knowing this from this video and this previously, we can differentiate this whole thing. And I've said before a couple of times about how, complicated functions could become very complicated in order to work out their derivatives by the limit definition. Something like this is to the point where that would be absolutely impossible. So it's exciting then that this is a very easy example. If you want to differentiate this guy, well, that's differentiating this thing here, where, well, this is going to be a chain rule problem. We're going to let the inside guy be the outside guy be x to the pi, and our inside guy u be x plus 2 to the x. So by the chain rule, the derivative of this guy is, well, we just take pi and then to the power of pi minus 1, the stuff on the inside, multiplied by the derivative of the inside guy, which we now know is 1 plus ln 2 times 2 to the x. And this utterly horrific function, we've not only differentiated it, but we've differentiated it very quickly and very easily. And that's how this works.